G'day guys, we've got an applications of differentiation problem for you here today. More specifically, it's to do with optimization. We've got a man that can row 6 kilometers an hour and run at 8 kilometers an hour. He has 10 k's out to sea and needs to get to a marina on the coast, which is 18 kilometers from the nearest point on the shore to his current position. Where should he land on the coast to get to the marina as soon as possible? So the first thing, guys, that I would urge you to recognize in this problem is that the question is asking us where he should land. The question isn't asking what is the minimum time that it takes the man to get from the boat to the marina. We've been asked what this position in particular is right here. So how are we going to go about solving this problem? Well, to start with, guys, what I'm going to do is I'm going to break the man's journey into two parts. I'm going to call it part A and part B. Now, we've been told that the man can row at 6 kilometers an hour and run at 8 kilometers an hour. So the next sort of piece of information we can add to our diagram is the length of time it's going to take us to get from the boat to the shore and from the shore to the marina. So to start with, we know he's going to be rowing from the boat to the shore. So that's 6 kilometers an hour. And if the distance from the boat to the shore is A kilometers, the time that it takes is going to be A divided by 6. Similarly, for the running part on the shore, he's going at 8 kilometers an hour. The distance is B kilometers. So we're going to just go B divided by 8. Now we can then set up a full problem and say, well, the time in total that we're going to spend getting from the boat to the marina is equal to however long the first part of the journey is, A, divided by the speed that he takes through that entire part of the journey, plus however long the second part of the journey is, B, divided by the speed that he carries through the second part of his journey. Now we can do the future versions of ourselves a favour by simplifying this fraction, putting both these two fractions in over the same base by, let's make it what's going to be 24. So let's put it over 24. So 6 4s are 24, we can go 4a, plus, now we've got 3 8s are 24, 3b. Cool. Now, so what we have to do now, guys, is set up an equation that is going to be able to give us the distance b and the distance a in terms of a common variable. So the way I'm going to go about this is I'm going to go about making the distance that the boat is on the shoreline to where he actually will land, that variable is going to be x for me. And as a result, our b value will be 18, subtract whatever x is. So if x is 5, this will be 13. Our a value, however, is going to be a little bit trickier to compute, but not that much. We know that this is the shortest possible distance from the shore, so this here has to be a right angle. And as a result, we can use Pythagoras to find A. So let's just go about doing that over here. I'm going to say, well, A is going to have to be equal to the square root of 10 squared, which is 100, plus x squared. And we know that B now is equal to 18 take x. So now we have A and B in terms of a common variable. What I'm going to do is I'm going to sub them both back into this equation here. So I have my time total in terms of a single variable x is equal to 4 times A, which is this thing. I'm going to put it in index form rather than carry the surd around. So I'm going to have 100 plus x squared to the power of a half plus 3 times 18 take x, all divided by 24. Cool. Now, so what I'm going to do is before we start to differentiate, I'm going to multiply out this bracket here. So now we've got our total time function in terms of a single variable x. What I'm going to do is I'm going to differentiate the total time with respect to x and set it equal to 0. We're going to then solve it so we can find what the x values are for our turning points to this function. After that, we can then use the second derivative test at those x values to see whether or not those turning points are either a maximum or a minimum. But let's not get ahead of ourselves. Let's just do the derivative of this total time function. So I'm going to use dt dx of this function here is going to be equal to, I can bring the 1 over 24 as a constant out, so I'm not going to have to worry about it when I do my derivative. So it's going to be the same as 1 over 24 times dx of this function here. So I'm going to go, well, it's 4 bracket 100 minus x squared all to the power of a half minus 3x plus 54. Cool. Now for all you guys saying, mate, why are you doing all of these steps? You could have gone straight through. Well, I'm trying to help people who might not be as well acquainted with the derivative as some other people, so you're going to have to bear with me. You can skip forward if you like. So from here, guys, we're just going to take the derivatives. So we still have that 1 over 24 out the front. But the tricky part with this one is taking the derivative of the half power piece at the front. This is the trickier part, and it's going to require the chain rule to differentiate it because we have a function within a function. For example, if we come over here, I can say that my outside function, I can have y is 4u to the power of a half, and my inside function u is equal to 100 plus x squared. Now, the chain rule says that if I have a function within a function like I've got here, I can have the total derivative, dy dx, can be equal to the product of the outside and the inside function multiplied together. So dy du times du dx. Now in this case, dy du is equal to 4 times a half is 2, u to the power of negative 1 over 2, which we can rewrite as being 2 over the square root of u. Now we can say du dx is equal to just the derivative of this, which is quite simple, 2x. So, with both of these in mind, I can put them into my formula, and I can say, well, the derivative of the first part is 2 over the square root of u, so 2 over the square root of u. Now, u, guys, is equal to 100 plus x squared, so I can reinsert that here. So 100 plus x squared, and then I'm going to multiply that by du dx times 2x. From there, I'm going to just do the derivative of that 3x, so it's just minus 3. Now let's put all of that in a bracket. So this can then be rewritten as 1 over 24 times 2 times 2 is 4, 100 plus x squared minus 3. Now we have to make that equal to 0. Cool. So our next step, guys, is we're going to solve for x in this function here. So it's just an algebra exercise. The first thing I'm going to do is multiply both sides by 1 over 24, and that's just going to zero it out. So we're going to have left over 4x over the square root of 100 plus x squared minus 3 equals 0. Now obviously we're going to take the 3 over to the other side, so without having to do another step of working out, let's just do that straight off the bat. So we're going to go equals 3. I'm then going to multiply my surd across, and I'm going to put it in index form again, just so it's easier to recognize. So I'm going to have 4x is equal to 3 times 100 plus x squared all to the power of a half. Then what I'm going to do, guys, is I'm going to divide both sides by 3, So I'm pretty sure I'll just do that off this one. So I'll get that 3, get rid of it. And as a result, we have the 3 is going to go down here. And then my next step is to square both sides. So I'm going to have on this side 100 plus x squared, and on this side I'm going to have 16 x squared over 9 is equal to 100 plus x squared. Cool. So what I'm going to do from here is I'm going to take the x squared over to the other side. So now we have 16x squared over 9 minus x squared, which I'm going to write as 9x squared over 9. So we can actually subtract this in the next step. And that's going to be equal to 100. So 16 subtract 9 is equal to 7. So I'm left with 7x squared over 9, and that's going to be equal to 100. We're going to multiply both sides by 9 and then divide both sides by 7, and we have x squared is equal to 900 on 7. And then x is going to be equal to the square root of 900 on 7, which is equal to square root of 900 is 30 on the square root of 7, which if we were to rationalize the denominator, we would get 30 root 7 on 7, which is equal to approximately 11.34 kilometers. Now, what does that mean? Well, it means that this value here, this x value that we've got in our diagram, is equal to 11.34 kilometers, which also means that this part here is equal to 6.66 kilometers. So the question is asking us, where should he land on the coast to get to the marina as soon as possible? So the answer that we could write, let's just write our answer here. So we could say that the man should land his rowboat 6.66 kilometers from the marina and jog the rest of the way. Cool. So as you can see, guys, the big parts of this is number 1, evaluating what you actually have to figure out. Here we're asked to be able to decide where this point is. The next thing I thought was important was dividing this journey into 2 parts, A and B. I then figured out how I could work out the time they spent doing each part of the journey by dividing the distances A and B by the speeds that he could accomplish whilst rowing his boat and then whilst jogging towards the marina. Once I had that, I was able to then use the value of the distance between here and where he's going to come ashore as x, and I could then compute both distances, A and B, in terms of a single variable. After I did that, I differentiated. The hardest part of this differentiation was making sure that we got this chain rule section right here. And then once we found the differential, we were able to then just use algebra and hopefully not make any mistakes to get through our solution to solve it. I usually find that if we write a little answer at the end, if you write a nice worded answer, if you have time at the end of the question, the teacher is in no doubt what you mean by your response, and there's no way that you can lose marks. It also shows the teacher that you know exactly what you've just figured out. So guys, I hope the video helped. If it did, give us a like. Subscribe to my channel. I'm going to try and put out new videos all the time, but let's see how that goes. But until next time, keep enjoying your maths. These problems are hard if you're seeing them for the first time, so just keep on practicing and eventually it will become intuitive.